So kicking things off quickly this afternoon with our first presentation, AI enhanced material discovery, pioneering personalized material design with generative AI. So our speaker is a full professor of computer science. He's a chair in machine learning at the University of Amsterdam. He's a Merkin distinguished visiting professor at Caltech, and he's also co-founder and chief AI officer of CUSP and CuspAI. And personal note, when I researched a bit about the company, I recognized, wow, they raised an amazing financing round very recently, and also won the godfather of AI and recent Nobel Prize winner Jeffrey Hinton as their board advisor. So I'm super excited to have him here. Please give a warm welcome to Max Welling.
So now I'm confused whether I should talk with this thing on or whether I should not talk with this thing on.
Take it off, I guess.
Really?
Yeah.
I'm not able to hear myself even. Well, maybe it's okay. Well, let's see. Let's just try it this way. Right, welcome everyone. So I'm going to talk about AI enhanced material discovery. And of course, the first thing I will have to talk about is this. Since yesterday, two computer scientists in AI actually have now won the Nobel Prize in physics. This came as a huge surprise. And I'm particularly excited about this, not just because Jeff is on our board, and of course I worked with Jeff for a few years as a postdoc. The committee wrote this. They said the laureates' work has already been of the greatest benefit in physics. We use artificial neural networks in a vast range of areas, such as developing new materials with specific properties, says Alan Moons, chair of the Nobel Committee for Physics. So they reference to the impact that this technology is having on the design of new materials for, in my view, a sustainable future. And then, just when you thought you had recovered from that blow, the next one comes. Today, there is another Nobel Prize, now in chemistry, where AI technology plays a key role. These two labs have pioneered the use of AI in designing new materials and also designing proteins and folding proteins. So congratulations to all of them, of course. It's an amazing achievement. By the way, my clock isn't ticking. It's still 20 minutes. I like that, but it's probably not what should be done. All right, so let's start the talk. So I want to start by saying that in the 1800s, the first revolution, the so-called industrial revolution, transformed society by mechanizing, if you wish, human labor. Now we are in the middle of another transformation, which is the digital transformation or the AI revolution. And of course, the two Nobel Prizes definitely do sort of help sort of underwrite that. My view is that the Industrial Revolution actually polluted the Earth, or was the root cause for a lot of pollution that we are now suffering from. In fact, climate change is somewhat of a result of the first Industrial Revolution. And now with the growing demand for compute, in fact, the Industrial Revolution is even demanding more energy. But there is also an opportunity to use AI to clean up the mess from the last revolution. And that's what we in our company, CuspAI, are focusing on. And so this is about Steve Jobs, another famous person, didn't win the Nobel Prize, but certainly was smart, very smart as well. He said this revolution, the information revolution, is a revolution of free energy as well, but of another kind, free intellectual energy. Basically that led to these sort of advancements. We can now generate images basically out of thin air, out of random numbers, by using sort of machine learning and AI tools. And of course, this is progressing as we speak. We can now generate images of dogs eating ice creams or playing in the snow. Highly realistic, I would say. And that's definitely amazing. It's not what wakes me up in the morning. It's these things. And in fact, this is, of course, where the Nobel Prizes were won. The left there, you have the protein folding problem, where today's Nobel Prize, in fact, was awarded for. Generating molecules, let's say drug-like molecules, where David Baker was instrumental as well for the Nobel Prize. And then another example here is keeping a plasma fixed inside a nuclear fusion reactor so that the plasma, which is very, very hot, doesn't actually hit the boundaries of that fusion reactor. Now, let me just try to explain to you what this revolution is that caused these two Nobel Prizes to be awarded yesterday and today. In my view, what is it that's changing in the way that we are doing science? And the disruption, I'm going to explain to you in two short steps. The first step is going from experiment to computer simulation. So in the old days, when people discovered new materials or new molecules, they would do a lot of lab testing, trying a lot of things in a lab and seeing what worked and what didn't work. Now later, of course, computers started to play an increasingly important role. A lot of data was collected. This data was stored in databases. Data analysis was done on that data, and predictions. People were trying to understand better what the experiments were saying and trying to come up with new and better experiments. So that what's happening these days, today, I would say, is different in the sense that the actual experiment is done in a computer. So in fact of actually waiting for an experiment to happen in a lab, you do it in a computer. You simulate the molecules directly from the laws of physics inside your computer and then read out the results. Of course, this you cannot do with a huge amount of molecules, but for smaller molecules, you can definitely do that. Of course, you need an insane amount of compute, which is what we are starting to see to happen. Now, the second step is perhaps more important even, which is what I call emulation. And emulation is when you, let's say, maybe best explained with an example. So let's say you've designed a car. That car you've put in the wind tunnel. It's actually a digital wind tunnel already, so you've subscribed to the last disruption in the previous slides. It's in a completely digital wind tunnel. And then if you come up with a new design, instead of going through exactly the same wind tunnel experiment, you've stored the data from the first experiment in a big database, and from that data you've trained models. These are emulators or surrogate models for which you can do the simulation much faster. You can do the simulation much faster, or you can directly predict the outcome of the simulation. And that's the second step of this disruption. And for instance, AlphaFold or force fields in chemistry are examples where this technology is used in order to predict the three-dimensional structure directly with using these machine learning models. Now, AI is now, we have seen Nobel Prizes in two categories. We've seen it in physics and chemistry, but we could go to biology, but we can go to astrophysics, we can go to high energy physics. It is making an impact absolutely everywhere across the entire spectrum of all the sciences, all the way from tiny particles at picometers to galaxies at light years distances. Now I'm going to talk to you today about two of these revolutions I've been involved in. The first one is in fluid mechanics, and the second one is in molecular mechanics, if you wish, or chemistry, which sits beautifully at the cusp of quantum and classical mechanics. So let's first say a few words about how AI has revolutionized weather prediction or meteorology or fluid mechanics, if you wish. And so this is maybe a few years old. When this revolution started, the meteorologists were deeply skeptical about it. How could a technique that is maybe a decade old disrupt a field that is maybe 100 years old of simulating forward using numerical methods, these partial differential equations which describe the atmosphere and from which we predict the weather. Yet around 2016 and 17, the first papers came out. that predicted globally around the entire Earth the weather patterns, including temperature, pressures, wind speeds, and many, many more things. So here are just 3 examples from Caltech and NVIDIA to Huawei and Google DeepMind on the right there. So this is a model that we developed at Microsoft when I was still working at Microsoft the last 2 years or 3 years ago. So this is called Aurora. This model is special in the sense that it can absorb any amount of data. So you have to understand the reason that this works so well is that there is an insane amount of data available in meteorology. We're talking about petabytes of data. So the meteorologists have been really good at storing all that data, which is why their field is actually being disrupted. These models have nothing to do with physics anymore. They're just giant neural networks, ignore all the physics, just giant neural networks predict the next weather state, which is a bit disappointing for a modeler, but there you go, that's what it is. And this particular model was developed so that it could incorporate any kind of data, high resolution data over America and the US, and low resolution data maybe globally, including all sorts of other measurement data. And in fact, in this particular model, we had over 1 million hours of weather data incorporated. It is about 5,000 times faster than numerical simulation. So there you go. At the accuracy, you can see this in these 2 plots there. You have to believe me. But the bottom line is the line that's the bottom 2 lines are actually the 2 machine learning models. Low is good. We are outperforming the best weather prediction models that use numerical simulators. And at a 5,000 times faster speed. So that's I think definitely what you would call a disruption. Now, people were particularly interested in this because it could go further than just predict the weather. In fact, this one also predicted air pollution, concentration of greenhouse gases, and a 5-day accurate global air pollution forecast at high resolution. So I would say this is disrupting our field definitely in weather prediction. Another field where these tools from machine learning have been disrupting science is in chemistry and molecular science generally. So here you see a molecule. It consists of atoms. Atoms are bound together by covalent and other types of bonds. One thing that you would like to do is evolve this molecule forward in time. You can use very old equations like Newton's equations, which are hundreds of years old, except there's two problems. One is chaos theory, which is it's very hard to actually predict very far into the future. The other one is you actually need quantum mechanics to predict the forces because the electrons are too small to be treated classically, and you need quantum mechanics, and unfortunately that is very, very expensive. But what people have done is that they have replaced, for instance, these computations that are for which you need quantum mechanics, there with the green arrow, they've replaced them with the large neural networks, again trained on expensive data sets, and that's called a classical force field or machine learned force field, and that's again orders of magnitude faster than what you would get if you would use the quantum mechanics calculation. I would say that's also worth almost a Nobel Prize. It's disrupting the field of chemistry quite a bit. So why am I excited about molecules? Well, molecules underlie about everything you can see and not see, except for maybe a few forces like gravitational forces and nuclear forces and electromagnetism, and maybe abstract things like your thoughts, which is more information states. Otherwise, everything else is made of molecules. So if we can control molecules better, we have a good chance of changing the world, hopefully for a better, to be a better place than it's now at, especially in terms of climate. Drug discovery is an important application of this. Solar cells, better lubricants, better catalysts to accelerate chemical reactions, for instance, for nitrogen fixation, which is for making fertilizers. And the one I'm particularly excited about is carbon capture, which is a material called metal organic frameworks. I predict there's going to be a Nobel Prize for that in the next few years to the inventors of metal organic frameworks. And they're very good at capturing carbon dioxide out of the air. But how do you design the best one is the big question. I just highlight a little bit all the places where machine learning has played an enormously important role in the sciences. For instance, here we see a beautiful illustration with these green blobs flowing. That is the quantum mechanical wave function, the electrons flying around a molecule. In order to simulate it, it's insanely expensive, and so machine learning methods have been used to simulate the Schrödinger equation. In the right next to it, where it says Langevin equation, you see molecules. You need to simulate them with quantum mechanics, but now you have to simulate all of them. We replace the expensive computation by force fields. And then on the right, we have two fluid mechanics problems, and in particular the weather prediction part. At the bottom, there's three important application areas. One is drug discovery. You can now design molecules in your computer completely automatically. And then we have catalysis, which is designing catalysts which accelerate chemical reactions. And then on the right, there is the design of new materials with prescribed properties. And I'll say a few more things about those. But first, let me say a few things about machine learning. So what are the models that are disrupting this field? Of course, with one figure, I'm not going to explain that, but at a very high level, the idea is to follow basically physics again. You start with a clean image and you start to noise it up. Like everything in life, if you don't do anything, everything turns back into dust, to high entropy states. Here we accelerate that by actually adding artificial noise to an image until it is completely noise. You then observe precisely what happened in that process. You try to invert time. You try to run the movie backward in time. Of course, this you have to learn. You have to train machine learning models to do that for you. And if you can do it, you can unscramble an egg. That's basically what's happening here. And then at the bottom, you can see how now a piece of noise, randomly generated noise, already? All right. Can turn into a beautiful image of a flower. Okay, we have generated molecules with this. In our computer here you see a little movie where a molecule is forming in the same way as an image of a dog is forming, but now an actual molecule that could be a drug molecule. Here's an actual drug molecule in your computer forming in the pocket of a protein. Okay, so what I want to say is we are at a very special time. It's a special time because a number of things are starting to converge. The first thing is that we have very advanced fields in molecular science, like molecular biology, computational chemistry, and condensed matter physics. The field of computational science, including machine learning and quantum computing, is up and coming. That's where the revolution is happening right now. And there's very important applications which are pulling on these technologies in sustainability, in energy, and in health. And we've named all the ages in which we live after the materials that we've used. And I predict that after the Plasticine that we live in now, we're going to have an age where we have materials on demand. So what we are building in CUSP is basically a search engine. You type a query, I want a molecule with these properties, a search happens, then there's a neural network that predicts the properties of the thing that you have developed and designed in your computer. Data goes back to a database, models get retrained, and the iteration repeats. If we accelerate this and we get better at this, we can very quickly search for new materials with desired properties. Last slide. So there is a very deep connection between AI and the natural sciences, and I want to say the Nobel Prizes yesterday and today have emphasized that. It's two ways, going from machine learning to science and from science back to machine learning. ML is a very powerful tool for the scientist. And in fact, these days you can win a Nobel Prize by developing a hammer like that, which is good news for our field, I think. And perhaps most excitingly, there's beautiful applications in healthcare and sustainability for new drugs and materials. I think it is very important because the world is in a dire place in terms of climate. This came out a few days ago, or maybe even today, I forgot. And it says, the state of the climate report, we are on the brink of an irreversible climate disaster. This is a global emergency beyond any doubt. Much of the very fabric of life on Earth is imperiled. We are stepping into a critical and unpredictable new phase of the climate crisis. If that doesn't get you worried, I don't know what should get you worried, but I think it's all hands on deck, and I think these new AI technologies could at least try to make a difference. Thank you.
Yeah, thank you so much, Max. That was a really, really insightful presentation. at least maybe one question, or although we are already quite tight, maybe one question from the group here. We have a mic. Mike, here. There you go.
Hey, thanks for a very nice talk. So in these classical ways of modeling things, you typically start out with an initial situation and then iterate until you have the laws of physics say, for example, that you've arrived at a solution. In these machine learning methods, do you still check using the laws of physics whether you've arrived at the situation, or you just ask the model to predict the right solution and accept that?
That's a great question. Both things are possible and both things are being done. So if you want to include some physics priors or biases, you typically want to do it step by step, and maybe with these force fields you replace the quantum mechanical calculation with a force field, but you still simulate step by step. But there's also methods which directly predict, let's say, the ground state energy without actually doing the relaxation, or predict properties of molecules without actually doing the simulation. So both things are possible. One is obviously much faster than the other, but also probably a little bit less accurate.
Perfect. Thanks so much, Max. I hope you still have a few minutes maybe left if some people still have some questions, if that's possible. Excellent. Thank you so much. Thanks again to Max.